Okay, good morning everyone. So, welcome you all for day 3, session 1. And today's theme for generative AI is basically on the generative text AI, where we are going to discuss the foundational model for uh, that that becomes the backbone for large language models and other text generation AI. So, during this whole session, we are going to see how started with NLP and then the language models and the transformers, how they come up together, and then towards the end, uh, the large language models have been uh, developed in recent time. So a little bit of so uh, first of all, the content credit goes to some of the authors, some images, and I found those images quite beautiful and easy to understand. So they are from from Jay's blog, and some of the explanations are adopted from Andrew Ng course Introduction to Sequence Modeling, and there is one resource that you can refer, uh, which proposes the attention is all you need in 2017. So, starting with background, uh, when we talk about natural language processing, so basically, unlike computer science, where we try to understand the computer language, this is a reverse task where we want computer to understand our language, that is human language or natural languages. So, it is a branch of AI which empowers computer to understand, interpret, generate human language in a way that both meaningful and useful. And broadly, it is divided into two areas: natural language understanding and natural language generation. So, and there are lots of applications of natural language processing. You might have seen Siri and Alexa that understands the command and give the response. Understanding the text in terms of emails, identifying whether it is spam or non-spam, which is classical machine learning task. And then one of the important, which is called machine translation, which translate input from one language to another language. And sentiment analysis, predictive text, autocorrecting, all are this comes under NLP task. So, and this NLP task have been core idea of generative text AI, and so all the models in generative AI, especially good for text, trained on vast size of dataset, and using those datasets, generative AI learns the pattern and style and structure that it uses to generate the novel output. So if you're using ChatGPT or any other LLM like Gemini or Grok, you just give a prompt and it come up with uh, entirely new and relevant content. So this session is not focused on NLP side, and there are various sub stages in NLP that we are not going to discuss. Since our core idea is to move towards LLMs, in this session we will focus on on only those parts that are important to understand the foundation of LLMs. So uh, one of the primary tasks in NLP is called language modeling. So there are three types of language modeling. So basically, if we talk about language modeling, is the core task in NLP that involves prediction of the next word in a sequence based on the previous word. So you have given some sequence. For example, consider this sentence only, this three primary type, and we want to predict what could be the next word here, let's say. So then the prediction of the next word is depend on the uh, previous sequence based on the previous words. That enables machines to understand the uh, generate human-like text. And there are three primary types of language modeling have been used in the field, and it is evolved in the natural language processing. The earlier have been started with statistical language models. One of the example is n-gram model, where this model predict the next word based on the previous n minus 1 words using statistical probability. For example, let's say if you are talking about bigram model, that is n is equal to 2, then this bigram model estimates the likelihood of the word given the immediate preceding word. For example, uh, in the sentence the cat is, and let's say in the training data it is followed by on, then in the sentence cat is, a bigram model might predict on based on the frequency of cat and is, and so on. And however, this statistical model are quite simple, but they are computationally inefficient. Where when you want to train or on a large corpus, so they are easy and simple for small data sets and small text. However, these are not sufficient for large amount of data. Then language modeling have moved towards neural language models, where these models like RNN and its variant like LSTM, GRU, BioLSTM, and so on. These models uses neural network, for example, recurrent neural network or long short-term memory network to learn the probability distribution of the word sequence. That captures more complex pattern than the n-gram models. For example, uh, an LSTM model trained on the corpus might predict, for example, sleeping after the cat is word. So the next word prediction based on the previous words. So these models can consider a longer context than the bigram model. However, this neural language models also have some limitations, which were overcome by transformer-based models. And that's where from the pre-trained language models have come into the picture. In 2017, in the paper called Attention is All You Need, Transformers uses self-attention mechanism to process entire sequence in parallel. So there are some limitations that have been moved towards the transformer-based models. And from transformer-based models, basically, this becomes, because the parallel processing now it is possible and the pre-trained models have been built over the transformer-based architecture, then various LLMs have come into the picture. So there are three. So in summary, there are three primary types of language modeling. We are in this session. We are mostly will focus on the foundation of uh, sequence to sequence models and what are the problems that we move toward transformer based model and what are the properties and the characteristic of uh, this transformer based model, transformer based architecture, which enables parallel processing and computation on a huge corpus of text data. Now, uh, behind every model that we had seen, there are three types of mathematical model. So they are trained on three types of tasks. One is next word prediction. So the models looks at the sequence, for example, the sentence mathematical model of natural, and then it predicts the most likely word that is going to be occur after this word. For example, the model is trying to predict what word comes here, and so it takes the sequence of these words to predict the next word. There is another type of uh, mathematical model called masked word prediction. So this involves basically hiding a word in the sequence. For example, you can hide uh, any word in the sentence and asking the model to predict what the word it should be. So, and in this type of model, which based on masked word prediction, it takes the context on the both sides. So the model uses the surrounding context to infer the masked word, what would be the likely word here. So this type of mathematical model helps the language model to understand bidirectional context, right? So because it takes the surrounding context to predict the masked word, and this model tries to understand particular word based on what comes before and what comes next. And there is another mathematical model called replace word detection, where in this task it involves showing the model a sentence where one word might have been replaced with an incorrect one, and then asking it to identify the potentially wrong word. So this type of model helps refine the understanding of what makes a sentence grammatically correct and semantically sound. So they are the mathematical models, how language models, whether it is a neural network based model or transformer based model, uh, this model learns the uh, semantic of meaning and the context of the semantic of the language or context of the language. By performing this, basically by performing this prediction and detection repetitively on a massive data set, so all those language models are trained on the vast amount of data set using any one of these tasks. Uh, the model come up with a sophisticated mathematical model that how the natural language works. So this is just a summary. What are the primary types of language model and what are the tasks they use to build the language model, right? So we are not going into the statistical modeling. We are more focused on the neural network based modeling. So to understand this, you have to uh, understand the sequence modeling. So unlike CNN or artificial neural network that you have seen and we had discussed in the session one, day one, session one, they take the input and using the hidden layer, you get some output. So there are lots of hidden layers depending on the how deep the neural network is. And towards the end, from the output layer, get the output. If you see here, the input uh, that you give to artificial neural network or other convolution neural network, we are more focused on the type of task where where sequence matters. However, this N and CNN does not have a uh, does not have the property to maintain the sequence of the words. So for NN, let's say we are giving a sentence, I like this movie as an input. So this is same as giving us like I movie this. So these models do not capture the sequence of the word or do not uh, maintains the sequence or ordering of the words. So that's why they fails to capture the semantic meaning and the context of the language, natural language. That's where sequence models uh, came into the picture, where uh, they maintain the word sequences. So there are various tasks in sequence modeling. You might have seen tasks like uh, in case of text, let's say sentiment classification, where your input is of some length, a sequence of text, and your output is whether it is positive, negative, or you might have a neutral category as well. So output is one, and your sequence is of n length. There is another task like NER, named entity recognition, that also uh, given a sequence, you want to predict whether with a particular word is uh, is an entity or not. So in that case, your input is a sequence, and your output is also a sequence. However, in this two, in case of any task, you can see the length of the input and the output remains the same. So for example, length of x is equal to length of y. There are some other tasks where, for example, uh, machine translation, which will be the backbone of understanding generative AI for text, where your X is an input sequence in one language, and your output is another sequence in some another language. However, in this particular type of sequence modeling, uh, your length of input and length of the output might not be the same, because a sentence written in one language might have different number of words compared to other languages. Also, there are some like music generation, where input could be it could be nothing, or uh, an integer might be representing the category or type of music you want to generate, and the y will be the sequence, which is the output, basically the wave sequence in case of music generation. So in sequence modeling, there are different tasks that you have, and depending on the task, you have different types of architecture. So just to give you brief idea how RNN captures the sequence, the model can be represented by uh, so NER means named entity recognition, name entity recognition. So I'll just give you a brief idea how RNN captures these ordering of the sentence or sequence. So, for example, let's to understand it, consider an example of named entity recognition, where you have an input and you want to predict whether this particular sentence have entity or not. So for example, your X is this movie was absolute amazing and so on. So your Y will be output. So this is not entity in case of movie is an entity and so on. And so depending on the word whether it is an entity or not, uh, it the NER captures, so the output input is processed. So how RNN works, so let me clear it and give you a better representation. For each input word, let's say you have an input X where it can be represented by X1, X2, X3, X4, X5, and so on. So these basically the words in the sequence. So RNN takes input. For example, this is your first input. It goes to RNN unit, and this could be simply a neural network where it has one input layer and hidden layer and one output, and that predicts the first output. However, uh, to check for second input, when it takes second input, it also takes the context vector from the previous RNN unit. It in some literature it might be represented by A, or some literature might be represented by S. So basically, this vector, which is an internal representation known as a context vector, which is fed into the second RNN unit, and based on this context vector and the current input, it produces the current output. For example, Y2. So that means that your Y2 is not only dependent on X2, it is also dependent on X1 as well. So you take the context vector which captures the context from previous input, and that predicts the output Y2. So for example, let's say you're trying to build a sentiment classification model, and your sentence is the movie was good. So the sentence to the RNA unit might goes over this, will goes to first RNA unit, and so these three dots representing the uh, a simple neural network with one input layer and then one hidden and one output layer, and it's give you the output. So this is your first input, and this is your first output. However, uh, in particularly sentiment classification task, your output for by reading all the sentence, your output either positive or negative or neutral. Let's say 0. So in that particular type of task, your this output does not matter. So what we do, we just capture input, let's say movie, and uh, it also takes context vector from the previous RNA unit and so on. And towards the end was good, and it predicts the final output, whether it is a positive or negative. So how you calculate this? So there, when you have heard, studied about the neural network, you might have seen that the input given to the uh, first hidden layer, it involves various weights. That weight you can represent by a weight matrix. So then basically there are two outputs you are getting. One is the context vector, let's say represented by A, and then output Y. So in this case, let's say if you are calculating A1, which is the context vector from the first Rn unit, is nothing but a weight matrix that is involved between input and hidden layer multiplied with the previous multiply with the input, which is x1 plus. Now each RNA unit is taking the previous context as well to generating the output. However, the first RNA unit does not taking any input, so we can fed uh, a random vector which is initialized randomly, might be zeros or anything. So that vector is also taken into the consideration to generate the output. So there is another weight matrix is involved, let's say denoting by WAA, and which multiply with A0. And you might have seen in ANN and CNN, we add bias as well. And the whole weighted sum and the bias we pass into some activation function to generate the output. So that A1, which is the context vector here, which we pass to the second unit, is calculated like this. And for the output, which is your prediction, is calculated by again the weight matrix involved between the hidden and the output layer multiply with the your internal representation that you have calculated by adding some bias and passing through an activation function. So we inside this, the dimension, how it is calculated and how it is done, I would suggest you to go into detail of RNN and CNN lectures. However, this is just an intuition how RNN works. So depending on the type of problem, you might have different architectures of RNN. For example, let's say one architecture is one to many, where you have an input to one RNA unit. So there is only one input which you gives to the first RNA unit, and you calculate multiple output. So this is your output one. Context vector goes to second RNA unit, and then you calculate the output two, and so on. Similarly, you have many to one, where you have many output like sentiment classification problem, uh, input one, basically the word one, and input two, and then input three, and so on. You might have n words in the input, and you finally towards the end you predict the output. Also, you have many to many. So many to many have two versions. If your input length and output length is equal, then it is as so you give first input, the first RNA unit, you calculate the first output, takes the randomly initialized context vector, and you pass the calculated context vector to the second RNA unit, and it take the second input and calculate the second output, and so on. So at the last, let's say this is xn, you calculate the yn. So this is many-to-many architecture where you have length of the input and length of the output 1. So context vector in intermediate RNN unit is basically the representation of the context, or you can say state, from the previous RNN unit. It is not randomly initialized. This vector, or basically this vector is, you can think of numerical representation of the context from the previous RNA unit. So for example, if you have let's say third RNA unit here, and you are calculating the output here. So this A2 captures the representation from X2 and X1. So it captures the context from all the previous sequence in the words from the sequence, and so on. So last vector, the last context vector will be capturing the context from all the previous uh, words in the sequence. So you can think of it as an internal representation. It is more of like similar to the context vector that we had studied in case of images in autoencoder, where context vectors capturing the numerical representation of an input. Initial vector is it is random, and you can define it either you can initialize with 0 or any other values. Mostly we initialize with some initialize with zeros. One of the main tasks in this, which we are basically interested, called machine translation, because machine translation is one of the basic tasks in generative AI, where you give input in one language and it produces output in another language. And throughout this discussion, I have not gone through many details that you can check. So you might have seen backpropagation algorithm in neural network, or basic neural network, and CNN. Uh, in case of RNN, we have a backpropagation through time, in short BPTT, which is backpropagation through time. So, for example, in the many-to-many task where you calculating the output, you calculate the loss by calculating the difference between predicted output and the actual output for all the units, and you take the sum of as equal to 1 to n of loss between each prediction and the actual, and you take the sum, and that becomes your total loss. And now you backpropagate uh, and update all the weights in the sequence of RN units in the backward direction. So you update the weights of internal RN unit of the last, and then moves backward. So you can think of this sequence as a time steps. So this is time step 1, time step 2, time step 3, time step 4. So that this is known as a backpropagation through time. And most of the things I have not discussed here. Also, one of the interesting type of RNN which is many to many. However, the length of the input and the length of the output is not same, might not be same, which is one of the tasks called machine translation. In that case, RNN unit might look like this RNN structure. So initially, you give first input to first RNN unit, and obviously a random context vector. And since you don't know the size of output, so that the structure have two blocks. One is called encoder, and one is called decoder. And then you pass it to the second, so context vector pass to the second RNN unit, and so on. However, you can see we are not generating any output here. We are just encoder trying to learn the context of the word. For example, this is your nth word in the one language. So input is given to one encoder architecture, which towards the end generates one context vector. And that context vector is basically capturing the state of the context of all context of the input sequence. And that context vector goes to the decoder unit, and decoder uh, each unit in decoder generating output by taking the input by taking the context vector as an input, and the second generates the second output, and so on. So in many to many version problem, you have a encoder decoder architecture for RNN, where an encoder encodes the input into one context vector, and that context vector becomes the input to the decoder part. So, okay, I hope you got the intuition of what is RNN. Yes or no? If you have any question, you can ask. How the training will be done? So training is done using backpropagation through time. So in many to many depend. So in case of the same, it will be done using backpropagation through time. You calculate the overall loss. Yes, length is not the same. Length of the input and length of the output is not the same. So you calculate the loss based on the actual output, for example, y1 and the actual y1 and the predicted y1. You calculate the difference. So loss 1, loss 2, loss n, and you take the summation of all the losses in the output unit. And that loss might be defined as a cross entropy loss or any other loss that loss function that you define, and then you backpropagate. Backpropagate means you update the weights of the each RNN unit in the decoder as well as in the encoder as well. Whether output from previous unit in decoder whether output from the previous unit in the decoder will be given as an input. So it depends on the task. So it might be given in case of encoder decoder architecture, not in case of another architecture like music generation, where output is also dependent on the previous input, then it can be given. So depending on the task we want to give. For example, here, let's say uh, we have music generation task. where the input is could be a single value or even a file. It depends. In some architecture, it might not be needed because basically the main input is your context vector from the encoder, not the output words. So output words are mainly dependent and mainly mapped to the input context vectors. So in machine translation task, it might not be needed because so you let's see this example. You will understand. Okay, so in case of music generation, you might need it where Y is the wave sequence, where output is in a sequence with respect to the previous output. So in that case, you give input to the first RNA unit and you calculate the output, and then this output is given to the input to the second RNA unit, and that generates the second output. Now in machine translation task, the output is dependent on the context vector from the input encoder, and that becomes the basic idea of how language models have appeared. So since I've already talked about machine translation, so this visualization gives you a better understanding how sequence to sequence model maps. So here you have encoder unit which have input in okay, which have an input in one language, and it is generating sequence in another language. So how it actually works? So given first input to the encoder, encoder generates the context vector, and that context vector is given to decoder to generate the output. And context similar to the that we had studied in yesterday in the first lecture. Context is basically the vector or array of a number. So this number captures the context from the sequence, input sequence, input sequence. Also, the input words that we are giving, though it is trivial to understand, the words you cannot give directly input to the RNA unit or any neural network. This word should be represented by a number. For example, you want to give this as an input to one RNA unit. This is basically represented by a vector, which is called word embedding. So initially words are converted into numerical vector that captures the semantic meaning. And for word embedding, you can use various uh, language models like word2vec, glove is there, fast text is there, elmo is there. Also model for which task? uh, did not understand your question. So any model for detecting artificial intelligence school word? I did not get your question. Can you elaborate? What do you mean? Instead of detecting artificial and it is okay. So in the corpus on which you are training, then you have to, so there are two things. One is artificial and intelligence coming together, right, in a sequence. So if your model in language model having a corpus where intelligence is frequently coming after the artificial, then your model will be able to capture that sequence. It will learn that sequence during the training. Now, the second way of what I understood from your question, that you want to treat it as a single word. Then single word you have to treat it. Then in your corpus of training, it should come it as a single word, not as two words. However, the important point is we want to capture artificial intelligence as together. So then obviously this sequence will be captured by the model when trained on the large corpus which contains artificial intelligence together. But if you are asking as a hard coding it, that okay, so we want artificial intelligence as a assuming as a single word, so then we have to assume that that word is a single, and then single word embedding we need for this. So whatever I just explained to you is explained here. So how RNN unit maintains the hidden state or context vector across the time step. So for example, hidden state 0 given to the Rn unit, and you have an input vector, again a representation of word in vector. It processes them and produces two output. One is the output and one is the hidden state. Next hidden state that is given to the next Rn unit. So time step 1, first input goes, encoder generates first hidden state and second hidden state and third state, and the last hidden state works as a context vector to the decoder unit, and then decoder generates the output. So encoder process each word sequentially and generate the hidden state or the context vector, and towards the last context vector is given as an input to the decoder. So, and that decoder takes the, so now you can see more elaborated visualization where decoder RN unit takes context vector and generate the output. So now connecting to the language models, where how this RNN can be used to predict next word. Unlike machine translation task, we are talking about language models, where language model capture the semantic meaning of the corpus. This RNN can also be used for language modeling and sequence generation. So what we can, so how the RNN is trained to build the language model. So we take gather the training data, which is a large corpus of targeted language text. Then we tokenize this training set by getting their vocabulary, and either you each one hot encoding do for each word, or you can generate a word embedding for each. And for each sentence, you add the end of sentence tokens to understand that where the sentence end. And if for any unknown words you put the tokens, it is just a pre-processing task that you. And For example, given the sentence, scientists discover a new planet outside our solar system, training time, this sentence will be used and given as an input. The output, basically, it is the probability of this word given the correct first word. So here in case of let's say y2, y2 will be the probability of the second word given the correct first word. So correct first word is this. So in this language models, yes, the input output of the previous words becomes the input for the second word. So here we are not translating it, we are basically generating sentence. So and then this becomes, and this is the output, the probability that you get the probability across all the words in the vocabulary, and you pick one of the word which has the highest probability. Similarly, probability of third word given the correct first word and the correct second word and so on. So to predicting the chance of next word, we feed the sentence to RNN and then get the final prediction, which is Y at the time T, and short it by the maximum probability. And this is same as computing probability of three words together by calculating the probability of first given multiply with the probability of second given first word and multiply with the probability of third given first and second word. And once this model is trained, we can generate new sentences or novel sentences through this model. So what we can do, we can pass any zero vector or uh, let's say initial word vector. Let's say you want to generate a word with starting with the. So you pass the word vector of the to first RNA unit, and then it generates the output by generating the next words in the sequence. Now, so there are various problems with basic RNN, which is so okay. Sorry, state means context vector. You are saying? So we are passing the context vector as well as the previous predicted word, correctly predicted word. In case of language generation, not in the machine translation, we want to generate new sentences. Like your chat GPT or LLM is generating word by word based on the previous words. So initially you can give any starting point. It could be a zero vector, or it could be a simply a random sample from the distribution, and whatever the output that you get is becomes your first uh, word to start with, or the next word from the first word that you have given. And this basically this output is come up from the uh, set of, yes. So probability, basically not exactly probability. So context vector is there. It is, this is right. So probability across all the words across in the vocabulary, and you pick let's say highest, the word which has highest probability you pick as an output. So for example, after the, you might have vocabulary, in vocabulary you might have cat, dog, horse, or moon, sun, and so on. And For each word you are having probability, like let's say 0.9 is cat, 0.7 is for another word, and so on. So you pick the word with the highest probability. That word is given as an input to the next RNA. So now you have learned the and the cat, and then this, the context of the goes from here and the cat as an input, and then you predict the next word, which again from the corpus uh, corpus or vocabulary, you check the probability for which uh, words is the highest, and you pick the correct word, and so on. So that's how it generates word by word. Okay. So now what I have not covered is RNN have one that there are some problems with RNN. One is the long-term dependency. So it fails to capture the long-term dependency because your context vector becomes the bottleneck. And there are some other problems with RNN, like vanishing gradient, which problems happens during the backpropagation time. So we have not covered those things. Also, to solve the vanishing gradient and to capture the long-term dependency, there are variants of RNN like GRU, gated recurrent unit, and LSTM. So if you have now, since you have the intuition of RNN, how RNN works, you can uh, study more about GRU and LSTM, how they tries to capture the long-term dependency, and how they avoid vanishing gradient using some more gates in the network. And so when we talk about RNN, we are talking about simple RNN, or known as a vanilla RNN. So there is an improvement of this basic RNN network in case of GRU and LSTM. There is another issue that we are moving from left to right in the sequence. So it generating an output at time t, uh, it have the context from all the previous words. However, it might be possible that, for example, this word t might be dependent on the future words, context from the future words. So the output should not only takes the context vector or state from the previous word, it should also get the context vector from the next word in the sequence. So for that we have bidirectional version of this. So bidirectional RNN, bidirectional CNN, GRE. However, okay. So now, how many of you understood the at least intuition of RNN? Then we will move ahead. They are primarily built for sequence modeling tasks. So in sequence, uh, where you have an input as a sequence, so it might be text, it might be an audio as well, it might be a simply music sequence also. So where sequence matters. However, they are primarily used for uh, text and text related task. So They were initially used for all the different text related tasks. However, there's there are some problems with these sequence models. One of the uh, problem was the context vector. That becomes the bottleneck. Now think of understand this. For example, you have an RNA unit, and here you whatever the context vector you get, this basically having the context vector of, let's say, these 4 input in the sequence. So this context vector, which is of a particular length, limited size, holding the amount of information about the previous all the sequence. So at one point of time, this context vector becomes the bottleneck, and it fails to capture the context from in the sequence. So that's why these RNN or variants, RNN and its variants fail to capture the long-term dependency, because this limited size of vector, context vector, becomes the bottleneck. So hard to retain all the input information, especially for the long sequences. So the idea comes for the attention was why we are taking. So for example, let's say I'm generating the output here, and that comes in the sequence, let's say 5, and the output, uh, for example, here input was cat, and here the output was, and the was or were, it might be depending on cat or cats. So the output of this is only dependent on the context information from this word. It might not be depending for the other words that might be, let's say, is, the, or any other words that are there in the sequence. So why we are feeding all the information into context vector and giving it to the this RNA unit? Why not just focus or give attention to those words which are important? So attention addresses this bottleneck by allowing dynamically focus on the relevant part of the input during the translation, instead of giving whole information as a context vector as an input. Because if you feed all the information in the long-term sequence, the context vector might forget, or might information, or might not retain the information from whole long sequence. Instead of, why not just focus on some part of it? So dynamic attention means network will dynamically learn that which word is dependent on which previous context. Instead of taking all the context vector containing all the information, why not just focus on uh, which part of the input sequence is important for the output, and how it is done? It is done is dynamically. The model learns during the training. So see this. So then attention mechanism comes into the picture. Similarly, same encoder decoder architecture. Instead of giving now the last hidden state, what so this is your sequence to sequence with attention mechanism that is introduced for capturing the long-term dependency. There is what are the changes? So encoder state, in at the time of encoding, input is given, and the hidden state that is calculated. Instead of giving the last hidden state, we give all the hidden states to the decoder unit, and each decoder unit takes this all hidden state and generate the output. So in that way, instead of focusing on one last output, it takes all the hidden state, and attention mechanism identifies key which one is important, whether first hidden vector or the second hidden vector or the last hidden vector. So all encoder hidden states are given to each decoding step, and it calculates the attention weights to emphasize important encoder hidden state H is decoding step. So now you understand. For example, this is your first decoding step at time step 4. So how attention is done? The input is given. Input is your 3 hidden state, and score is calculated. So we calculate attention score on this hidden state. How it is calculated? We have mathematics in upcoming slide. You just assume that okay, somehow we calculate the score, and that score means the hidden state 1 is important, and so on. So based on the how much attention to be given is we calculate the attention weights, and these attention scores is squashed between 0 and 1 using softmax function. So that gives you the score, and then this score is multiplied with the hidden vectors. So that basically give the intuition ki, okay, so high the one which have highest so score, the vector is more important and other are less important, and the summation basically gives you the context vector for decoder at time step 4. So that context vector majorly holds the information about the uh, hidden step which is more important. How many of you understood this? The decoding side, first decoder at unit takes all the hidden vectors. Let's say previous example, we have 3 hidden vectors, and somehow that why I'm saying somehow we'll see how we calculate this. Somehow we calculate this attention weight, and we squash this attention weight in between 0 to 1, so that using activation function, he has using softmax, and that score basically intimate that okay, so which hidden state is important, and if we just add it, basically this output vector context vector is having the maximum information from uh, particular hidden state. So basically, which means that uh, so when you take this hidden states, so you calculate the attention mechanism, you get the context vector. So that context vector and hidden state that you have calculated for one particular output, you concatenate both and you generate an output. Let's say generating output is I. So that means that I was related to first hidden vector, in particular this example. And during next time, this uh, again attention vector is calculated, and optionally the input of the previous output is given, and then hidden state is calculated, and here also again the context vector is calculated to generate the output. And similarly in this next uh, unit, the attention mechanism. So now you can see in the time step 5, the second hidden state was important to generate M. So this is how attention mechanism is used to find out the relevant information in the vector. So that using the attention weights, you are dynamically identifying which hidden state is important, or basically intuitively which input was important to generate the particular output at particular time step. So let me know if you want to I mean, have a recap of it, or any part that you have not understood. Okay. So is this part is clear? Why uh, why this context vector is bottleneck? Okay. Now, so the whole objective was capturing the whole information from the previous sequence. Why not? It might be possible, let's say, in one particular language, uh, for example, output in one particular language, I am a student. So I might be mapping to one particular word, which is in another language. For example, मैं एक स्टूडेंट, मैं एक विद्यार्थी हूँ. Okay, let's say. So I might be mapping with the word "मैं" only. So why we are instead of capturing the context from all the words, we know that this I is relevant to only word "मैं." So that's where attention mechanism comes. So instead of calculating, giving the last final vector, what we do at each decoder unit, we give all the hidden vectors, and some calculation is done, and we identify which hidden state is important to generate particular output. For example, here the attention decoder unit is generating I is basically dependent on J. So now how each RNN decoder attention, how each decoder unit calculates. So what it does, it takes all the hidden vectors, and somehow that we are going to see how it is done. Somehow it calculates the score that which hidden state is important. That is known as attention weight. That attention weight, to scale up between scale to scale it or normalize it between 0 to 1, we squash it using softmax function. So that gives you output in between 0 to 1. So the highest value gives represent that, okay, so which particular hidden state is important. In this particular example, 0.96, that is hidden state 1 is important. And since when we multiply this score with the hidden state, which is again a vector of numbers, um, this becomes near to zeros or smaller values, and the uh, higher values are those which have the hidden vectors, which is the important. And to get one context vector, we just add those vectors. So basically, the at the end, the context vector that you get contain mainly the information from the one of the hidden vectors which is important, or one of the context vector, one of the state which is important. And now since we have calculated which is what is the context vector and which contain the particular information about which part of the sequence needs to be attended. We how does calculate the timestamp? Okay, okay. So step number 5. Okay, step number 5 is just add this because see after applying softmax, these smaller values, if this is multiplied with these vectors, so eventually the values of these vectors will be lower down, let's say near to zero or near to smaller values. So smaller values means less information, and the vector have higher values, basically have the more information. And to just get a single value, we just add it. These are just added to give one single context vector. And that one single context vector is added to hidden state and you get the output. I. And in the next RNN unit, that becomes the input. Uh, and again, the same thing is done to calculate the attention mechanism for this. And the second output is calculated. And so on. So I hope you now you have some intuition about attention mechanism. Any question? So here you can see here we are multiplying the results to the context vector to get the important one, and we just add this, so we get a vector which is nearly same to this because other was near to zeros or the smallest values. Is it clear? Yes, hidden vectors will be same for each RNN unit. So we gave the hidden vectors to all the RNN units, or all the decoder units, and each decoder unit will calculate which hidden step is important to generating particular output. So instead of giving the last hidden, context vector, it takes all the hidden vectors and it is given to each uh, RNN unit. And from those vectors, attention mechanism find out which uh, hidden state is important and relevant to generate the output in the current decoder unit. So how this mechanism works? End-to-end FC, we give the input embeddings encode to the encoder. We collect all the hidden states. We give to attention decoder, and then the output is generated. Uh, in the long term sequence, this can be there are some variations like global versus local attention, where to generate one particular output, you can take all the encoder state, or you can attend to some window. You take a window and you can take the only those hidden state which are around inside the window. So that one is a local attention. Now, this means that, okay, so hidden state corresponding to input in so one word you have one hidden state and so on. So that heat map shows that for word I, hidden state 1 was important, for M, hidden state 2 was important, and for output third, hidden state uh, 2 and 3. So that heat map shows the intensity, shows the of the color, shows the how much it is important to that particular word. And for the last output, hidden state 4 is important. So that heat map helps you to interpret the model behavior and basically the interpretability of the model. So in one language, you have a text in another language. So that shows that, okay, so for word economic, the hidden state of this is important. But there are lots of application of sequence to sequence, machine translation, question answering, speech recognition, conversational AI, text summarization, grammar correction, code generation, and subtitle generation. There is still problem with this attention sequence to sequence attention mechanism, and due to those problems, we have moved to transformers. One of the problem is uh, still it is slow, computationally slow. Why? Because encoder unit is taking computing one RNA unit at a time. So first RNA unit take the input and then generate the output, and then vector is given to second. So sequence to sequence it is generating. Also decoder also, although it has attention mechanism uh, to mitigate the bottleneck and to mitigate the issue with the long-term dependency, still one output is generated, then the second output is generated, then say third output is generated. So it is slow. So when we talk about deep learning and when we talk about GPUs, uh, when we say this particular algorithm is computationally efficient, and behind the scene, all those libraries of deep learning that run the code on GPUs, basically they do the parallel processing of the input. So in this particular example, in this particular sequence to sequence models, the parallel processing is not possible. Why? Because it is generating output in a recurrent manner. So one output is dependent on the previous outputs, on the previous inputs. So it is generating sequence by sequence. So then the transformers have come into the picture where it has the property of attention mechanism where we can only focus on the relevant part. However, we want to do all the computation faster. No, it is calculated. It will be calculated because why it will be calculated? Because attention weight that is calculated at each time will be different. In some case, it might be 9, 13, or 8, or any other output. That how attention weight is calculated, you will understand in the transformer part. Because attention weight will be different, so that's why software source will be different, and that will give the idea which part is important. So moving from sequence to sequence modeling to transformers, the motivation was to make our model computationally efficient, still capture the sequence of the input, and however we want an alternative way to process the data so that it should not go one by one. It should be done in parallel. So we need an alternative way to doing those computations and also focusing on the important relevant words in the data. That's where transformers comes into the picture. Taking a 1 minute break. If you have any doubt, you can just uh, uh, write a message on the chat, and I will give you response for all the questions. Mm. Okay. So, should we resume? Okay. Talking about transformer, uh, the computation that we need to be faster. Transformers improve our RNN using self-attention mechanism, and that is the foundation of modern NLP models. Also, uh, we might not be able to cover whole transformer topic in this session. So whenever I will end, I will again restart in the session number 3rd. So in the hands-on session, before starting the hands-on, we'll have a session on the remaining part of this transformer, right? So this transformers are basically the deep learning models that uses self-attention mechanism to process the sequence. So because to address the limitation of the previous models like RNN, where the was uh, all the RNN units were processing each sequence in a step-by-step manner. And whereas transformers can handle entire sequence at once, and that is due to the self-attention mechanism. So this makes them faster and more efficient, especially for the long sequences. If you have long sequences, then uh, RNN or other models are are computation is slow because of that they are recurrent nature. Transformer taken all the sequence at once and it can process at once. And this transformer is basically the backbone model of all the uh, all the NLP models like BERT, GPT, and T5, and all the LLMs in the backbone have the transformer. So So RNN and their variants like LSTM, they struggle with the long sequences, and there is another problem called vanishing gradient. It happens when uh, in the long-term sequence when backpropagation is done, some of the weights are not updated. So due to this problem, though this problem is avoided by the LSTM, but the problem with LSTM is it produces the output of the same length as an input. So for machine learning task, it might not be suitable, though padding we can use, but still it is not suitable. Also, main problem with is this encoder decoder architecture that we had discussed in the previous session, previous slides. They struggle with the long range dependency, which is due to the context vector bottleneck. However, it is removed, however, it is tackled with the attention mechanism at the decoder side. Here an example given that when Sarah, a brilliant software engineer, discovered a critical bug in the system, she words is basically dependent on the word Sarah, which is quite far away in the sequence. So to maintain the long range dependency, uh, we have solved it using attention mechanism. However, still uh, it requires the sequential processing, and this is the main motive moving towards transformer. So we want everything that is there in the good thing in the sequence models. However, we want to avoid a bad thing, which is sequential processing. So instead of calculating one by one, transformer calculates everything in parallel. So this issue is solved using self-attention mechanism, which enable parallel processing of the sequences. So now the input is given to the transformer and the output is generated, and that transformer, whatever the operation that are inside the transformer can be done in parallel. This is an architecture of transformer, and though we have a lot of things to understand, I'll end it here, just giving you the idea of intuition of architecture. So it also has encoder decoder unit. Encoder unit takes the input and it takes the input embedding all the input at once. Now what in RNN what happens, you take one word at a time and then you generate the output, and then based on the context vector the second unit computes. However, all the inputs in transformer, what we are doing, we are giving at once. So due to giving at once, it cannot maintain the ordering of the words. So to maintain the ordering, or to make to add the position awareness, we use positional encoding and we add it with the input embedding. And then you have multiple times of two unit called multi-head attention, or basically self-attention, and the feed-forward network. And you can replicate this multiple times. Like in CNN, you have seen convolution pooling operations can be done multiple times. Here, attention head and the feed-forward, this operation can be done in the multiple times. And towards the last, output is given to the decoder unit. So decoder unit, it takes the output embedding and add the positional encoding. And here also we have instead of normal self-attention, we have a masked attention mechanism, and then we have multiple attention head and the feed forward, and after some operations we get the output probabilities. Okay, so what is the purpose of positional encodings. Positional encoding is important, though we are going to discuss again in detail, just to give you idea. So what happens, RNN intuitively captures the sequence idea, because first word is given and then the second word, when it is given to second RNA unit, it has the context vector of the first. So position is inherently captured. The sequence is inherently captured in RNN or its variants, because when it is generating the output for second RNA unit, it has the context vector of previous RNA unit. It means that it has already been calculated, and this output is generating after the output of generation of after the computation of the first word. So sequence is captured. Okay, so in simple RNN or simple vanilla RNN or uske variant mein, we go from left to right. In bidirectional RNN, we take the context vector from both the sides. However, whether it is a vanilla RNN or bidirectional RNN, we know that okay, so this output is based on the sequence from left, or if it is bidirectional, sequence from left and right both. So we know inherently we know the ordering of the words. So model is aware of the ordering of words. However, in case of here in transformer, we take whole input. For example, the sentence is I like this movie. So corresponding to I, we have a word vector. Like we have a word vector. This we have word vector, and movie we have this. So instead of RNN, where you take I first vector, then you calculate, and then for corresponding like you calculate, that maintains the sequence. What we do, we take all the vectors together for the encoder unit in transformer. So when we collect all the input vectors together and as a thinking of it as a matrix, and we give it, that we are going to discuss, that we are going to discuss how it is done, that we are going to discuss. So since we the time is up for the session, I'm stopping here, and everything will go into the detail of self attention, multi attention, how this the outputs which is shifted right, and everything in detail in the session third. So in the upcoming slide, you will understand everything related to this. So we are stopping here. We will have a 15-minute break. Yes, it is added to make sure the what is the position of that embody. To have the awareness about the position of the word, because we want to, because let's say, so again the examples are there. Thinking machine, example, there is one example, thinking machine and machine thinking are two words having two different meaning, and the sequence might be matter. So to make sure these two have a different embeddings, we add the positional encoding to have the difference between the order of the inputs. So the problem that we had in NN, where you can change the order, it does not make uh, uh, does not help or does not matter where you give I here, like this movie, or like here, and so on. We want to have a positional awareness of the word, from which position it comes. So that's why we are having uh, positional encoding. Okay, so You can, yes, we towards the end of this, even we will go till LLMs in this, in the continuation of this lecture. Though vision-based transformer is not in the scope of this particular session, but okay. So in upcoming session, somewhere I will add those at that part to give you an idea about. Because the whole idea, whole motivation of this presentation was to how we have moved from sequence modeling to the GPTs or the LLMs, and what are the in between technological shifts we have. What are the problems with language models, then statistical language models, then we came to the neural network based models like sequence to sequence modeling. The problem with those models, then we go into attention based mechanism, but still the processing was in sequence. Then we move towards the transformers, and then from the transformers, which becomes the backbone, we have come up with various pre-trained models. Unlike images where we had pre-trained models for CNN or other uh, image-based computer vision tasks. In text, specifically after the transformers, pre-trained models have become popular and have been used in various language models. Okay, so you can write your questions in the chat. Meanwhile, when I will join in third session, we will have a response to all those questions, and we will move ahead with the transformers and the introduction to GPTs and. Okay, thank you.